Hello everyone, welcome back to my channel. I'm Nandini. Again, I'm here to explain you about pumping lemma and its applications under the subject automata theory. Introduction to the pumping lemma. Let us know the definition of the pumping lemma. The term pumping lemma is made up of two words, that is pumping and lemma. Pumping. The word pumping refers to generating many input strings by pushing a symbol in an input string repeatedly. Lemma. The word lemma refers to the intermediate theorem in the proof. And there are two types of pumping lemmas that are defined for regular languages and context-free languages. The pumping lemma is a fundamental theorem in the formal language theory used to determine whether a given language is regular or not. It provides a set of rules to examine the structure of a language and identify patterns to prove non-regularity. The pumping lemma is often used to prove that particular language is non-regular. A proof by contradiction may consist of exhibiting a string of the required length in the language that lacks property outlined in the pumping lemma. Understanding the pumping lemma for regular languages. Theory overview, application approach, and real-world examples. The pumping lemma concept is based on idea that every regular language can be divided into prefix, a repeating segment, and a suffix which can be manipulated to demonstrate non-regularity. Application approach. Understanding proper segmentation and manipulating the segments to create non-regular patterns are key steps in effectively applying the pumping lemma. Real world examples. Practical demonstrations of using the pumping lemma will enhance the understanding of the regular language structures and associated patterns. Pumping lemma for regular languages. Theorem. If A is a regular language, then A has the pumping length P such that any string S where S is greater than or equal to P may be divided into three parts. S is equals to X, Y, Z, such that the following conditions must be true. That is, X, Y dash Z belongs to A for every I is greater than or equal to 0. And second condition is modulus of Y is greater than 0. Third condition is modulus of X of Y is smaller than or equal to P. In simple words, if a string Y is pumped or insert any number of times, the resultant string still remains in a. Pumping lemma is used as a proof of the irregularity of a language. It means that if a language is regular, it also always satisfies the pumping lemma. If at least one string is made from pumping, not in a language A, then the A language is not regular. We use the contradiction method to prove that the language is not regular. Steps to prove that the language is not regular using pumping lemma. Step 1. Assume that language A is regular. And step 2. It has to have a pumping length, say P. Step 3. All strings longer than P can pump S. Modulus of S is greater than or equal to P. Then step 4. Now find a string S in A such that modulus of S is greater than or equal to P. Step 5. Divide phi into XYZ strings. Step 6. Show that XYZ does not belong to A for same I. And step 7. Then consider how S can be divided into XYZ. Then step 8. Show that the none of the above strings are same and the three pumping conditions simultaneously. Step 9. S cannot be pumped. That uh, equals to contradiction. Applying the pumping lemma to prove a language is not regular. Pattern identification, segment breakdown, validation process. Let us see what is pattern identification. Recognizing repeating patterns and manipulating the segments to validate non-regularity. Segment breakdown. Analyzing and breaking down the segments of a language to identify non-regular patterns. Validation process. Using the rules of the pumping lemma to validate and prove that the language is not regular. Examples of using the pumping lemma to prove non-regularity. Demonstration 1. An example showing the breakdown and manipulation of language segments to validate non-regularity. Demonstration 2. A second case study demonstrating the application of the pumping lemma to identify non-regular patterns. Demonstration 3. Another real-world instance showcasing the effective use of the pumping lemma to prove non-regularity. Next, let us see the limitations of the pumping lemma, finite language scope, and complex pattern recognition. Let us know what is finite language scope. Discussion on how the pumping lemma may not be applicable to all types of languages, particularly non-infinite languages, and complex pattern recognition. Exploring the challenges of identifying non-regular patterns in intricate language structures using pumping lemma rules. Let us see the extension and variations of the pumping lemma. Generalized lemma, a broader version of the pumping lemma that allows for analysis of non-regularities of a broader class of languages. Advanced applications, exploring advanced variation of the pumping lemma, delivering into more complex language structures and analysis. Let us see some of the applications of the pumping lemma in the formal language theory. Language research, automata analysis, computational complexity. Let us see the language research, discussing how the pumping lemma is integral in the analysis and understanding of diverse language structures. Automata analysis, examining the relevance of the pumping lemma in the study of automata and their language interpretations. Computational complexity, understanding how the pumping lemma contributes to the comprehension of computational complexity in the language theory. Let us see the conclusion and the key takeaways of the pumping lemma. In the conclusion, the pumping lemma is a powerful tool in the formal language theory that helps demonstrate the non-regularity of languages for regular grammars and the non-context freeness of languages for context free grammars. It highlights the limitations of these grammar types and is the valuable proof technique in formal language analysis. And core insights, practical implications, and future directions. Core insights, summarizing the key insights gained from the study of the pumping lemma and its application in language theory. And practical implications, understanding the practical implications of the pumping lemma in determining regular and non-regular languages. Future directions, discussing the potential future advancements and adaptations of the lemma in the formal language theory. Thank you for watching. Please do like, share, and subscribe.